Hi everyone. Good morning, good afternoon, good evening, depending on where you are joining us from. Welcome to this webinar series on machine intelligence and modern infrastructure. Today's topic is pretty interesting. I'm going to walk you through the process of building serverless ML API hosted on AWS Lambda. So if you are attending this for the first time, let me set the context. MI2 stands for Machine Intelligence and Modern Infrastructure. Basically, machine intelligence is all about IoT, AI, edge computing, and, and deep learning. Modern infrastructure revolves around Kubernetes, microservices, service mesh, observability, and so on. This series primarily focuses on the convergence of machine intelligence and modern infrastructure. So today's topic is pretty interesting. This is the perfect combination of machine intelligence and modern infrastructure. On one side, we have a serverless infrastructure layer in the form of AWS Lambda, and running on top of that is a workload, which is a machine learning API. So that's about MI2. Now, in terms of agenda, I'm not going to introduce what is AWS Lambda. That's not the objective. This session assumes you are familiar with Lambda, and I'm going to start off with AWS Lambda as a serverless platform and some of the inherent capabilities and also challenges when hosting machine learning models in Lambda. And then we'll understand how to add persistence through Amazon Elastic File System or EFS. And then I'm going to walk you through the high-level architecture involved in hosting deep learning models trained either in PyTorch or in TensorFlow in AWS Lambda. Then I have a very comprehensive end-to-end demo where I will show you how to create an end-to-end environment all the way from training the machine learning or the deep learning model, deploying it, and going live with an API gateway front-ending that. So before I go any further, let me take a quick poll to make sure you are able to follow the presentation. So if you have any difficulty, this is the time to let me know. So please take a minute and click on one of these options. Is the AV experience good? Perfect. Perfect. Looks like we are on the right track. Thank you for participating in the poll. Now, let's get started. This is going to be an interesting session. Now, AWS Lambda is one of the very early, in fact, the first serverless platform launched in the public cloud environments. It brought many capabilities. Initially, it was just AWS Lambda. Then Amazon added the concept of step functions where you can stitch together multiple Lambda functions. And then they added layers through which you can bring in additional dependencies into AWS Lambda. They added multiple languages. So it has been growing phenomenally in the last 5 or 6 years since its launch. But one thing that always remained to be a challenge is adding state. Typically, functions or serverless platforms are completely stateless. That's because you are expected to deploy a function that will scale automatically. Now, there is a concept called scale to zero, where if there is no invocation, the resources that are allocated to this function will almost become none. So that is called scale to zero. And as and when the traffic spikes, there are more number of instances created behind the scenes, and you never have to provision any infrastructure. Now, the moment you bring in state, you automatically limit the ability to scale and elastically expand and shrink the instances. So that's the reason why traditionally state has been maintained external to AWS Lambda. So typically, when you want to maintain some state, for example, you want to process some input and save it as a PDF, you'll actually target an Amazon S3 bucket. So S3 bucket is a very popular and powerful combination where you either feed the input to a Lambda function or you get the output from a Lambda function to be stored in an S3 bucket. This is one of the very popular choices. Then, of course, there are multiple data services like Amazon RDS, DynamoDB, Aurora, and a whole range of SQL, NoSQL databases that AWS offers. So you can easily package the driver if it is not available within the Lambda default environment, and you can pretty much target any endpoint offered by the AWS data services. One of the other techniques that a lot of Lambda developers use is to target /temp directory. But I put an asterisk there because it's not a permanent, persistent option. Whatever is written to /temp is going to be vanished or becomes unavailable next time when the function restarts. So it is not a shared storage, or it is not a long-term persistence choice. But if you want to quickly do something, for example, you want to download a zip file, unzip that, and process every file in the zip file and write it to S3, /temp could be a potential target to expand the zip file and process. So it is typically a scratch disk, but it's not a long-term or a persistent storage choice. More recently, this was in June, Amazon has added EFS. So EFS is the elastic file system, and it's a distributed file system, which is almost like an NFS share that is available to multiple AWS environments. So earlier, without EFS, you had to launch an EC2 instance, configure an NFS endpoint on that, and then export that share and mount it in a variety of environments. But that was only confined to a set of environments. Typically it could be the EKS clusters running Kubernetes, or it could be EC2 machines running typical VMs. But beyond that, it was very difficult to share any distributed or a shared file system. Now, Amazon EFS solves a problem by offering a managed NFS file system for both cloud as well as on-prem resources. And because this is exposed as an NFS compliant share, you can easily configure an on-prem server to mount the remote cloud-based NFS file system. And this becomes the same persistent storage layer cutting across your hybrid cloud, all the way from your on-prem data center to the public cloud. So it's a very powerful, very useful storage choice when you are moving legacy applications. So this is typically used when you are lifting and shifting workloads from your on-premises environment to the cloud. So there are two storage classes like S3. One is standard, the other one is infrequent access. So infrequent access is obviously cheap, and you can also create some kind of a life cycle for files where if you don't access the files for a longer time, they'll automatically get moved into the EFS IA storage class. And this is going to be cheaper and will save you a lot of cost on using EFS. It also automatically scales to provide dynamic storage capacity. Obviously, it's a managed service. Just like S3 gives you literally unlimited storage, EFS also gives you a file system that has no upper limit. You can basically mount it and start dumping files and creating content, and it automatically and dynamically scale. It can be accessed from a variety of AWS resources, not just confined to EC2. Of course, EC2 is a popular choice because it all starts from the workloads running inside VMs, but it can be very easily get extended to Lambda. Recently, as I mentioned, I think in June or July, AWS has added the support to mount an EFS file system in Lambda environment. And this opens up a lot of opportunities that actually brings stateful capabilities to Lambda, and we can do very interesting things with that. Cloud build, which is the build environment, can also mount EFS. So it's again a very powerful option where you can generate artifacts and images and write them to EFS without actually launching an EC2 instance or a compute environment. So cloud build is also a consumer of EFS, and anything that you build can be persisted to an EFS backend. And of course, SageMaker. So if you are using SageMaker notebooks, you can always use Boto and the shell commands to basically mount an EFS share and directly target your Python artifacts and Python output to the EFS share. So all these are pretty capable choices of using an EFS backend. But in our case, we're actually going to use the combination of EC2 and Lambda using the same EFS file system. So here is what I'm going to build by the end of this session. So we are going to first create a managed EFS file share, and then we're going to mount that inside an EC2 instance. Now, this can be a SageMaker environment as well, but I want to keep this simple. So I'm going to launch an EC2 instance and mount the EFS share inside the EC2 instance, and we're going to make it available at /mnt EFS fs1. Now, once this directory becomes available, we'll move the train models and the labels to this location. And of course, all the dependencies. For example, if you are using TensorFlow or PyTorch or scikit-learn, any framework, any toolkit, you can use pip to basically dump all the dependencies in this file share. And then the same file share is going to be exposed to Lambda. So whatever dependencies you need for the model, for the inference, they're all going to be dumped inside this /mntml, which is again pointing to the same location. And then we will load the model as if it is locally available, but the fact is it is actually coming from an EFS file share. And once we write this model, we are going to attach an API gateway trigger and expose the inference API. And after this, you can basically hit this endpoint and perform inferencing on the fly. Now, the beauty of this architecture and the approach is AWS Lambda will always pick up the most recent version of the model. For example, every time the accuracy drops and we somehow detect the model getting drifted and becoming inaccurate, we can kick off the training process on EC2 or a cluster of machines running EKS or a SageMaker training environment, and then dump the most recent model again to EFS, which gets picked up by AWS Lambda. So it becomes a seamless ML ops pipeline to train and move the model to inference. We are not using Docker containers. We are not using any sophisticated techniques here. It is basically a file system, which is always going to contain the most recent version of the model. And that is what is going to be used by Lambda. So EC2 trains and dumps the model. Lambda picks up the model, uses it for inference, and exposes that via the API gateway. So to go further into the details, I have documented this step. So what are we going to build? Well, it all starts by creating a EFS file system. So the EFS file system is like a slice from the managed service that Amazon is exposing. Now, once we create the EFS file system, we're going to mount it within an EC2 instance, and it becomes visible there. And right after that, we're going to install PyTorch targeting the EFS directory. So when we use pip install, there is a mechanism to deploy the modules, all the libraries and all the Python wheels in a specific directory. So we're going to make use of that. If you don't want to do that, you can also use Python virtual environment. So create a virtual environment in the directory that is pointed to EFS, and automatically all the dependencies will get deployed there. So we are going to do that. Then we will train an image classification model within the EC2 instance or outside of EC2 instance. That is completely optional. Now, to save time, I have a pre-trained image, so I'm not going to really kick off the training. And then once the model is generated, we'll obviously move it to the EFS directory, and that completes the first step, basically this part where the model gets trained and becomes available on EFS. Now, the second part starts by launching and configuring an AWS Lambda Python function. So as we launch this, we're going to do a couple of things. First, we will mount the EFS directory within the Lambda environment so that it becomes available to our Python function, and PyTorch and the model become available to the Lambda function. And then we're also going to create a couple of environment variables pointing the Lambda function. For example, the Python path environment will force the Python runtime to look up in a specific directory. So we'll use Python path as the mechanism to point the Python runtime to the EFS directory that has the dependencies and also the model. And once we thoroughly test the Lambda function, we're going to attach an API gateway, and we will use curl to invoke the API. So those are the steps, but there are some nitty-gritties that we are going to discuss as we go along. So it's a pretty interesting scenario, and it opens up a lot of avenues to do interesting things with the combination of SageMaker and Lambda. So let's get started. Now, let me walk you through the environment first. So here is my AWS console. And as I mentioned earlier, it all starts by creating a file system. So I'm going to create a file system. Let me call this MI2. And obviously, when you're creating an EFS file system, you need to launch it in the context of a VPC. Remember, the consumers of this EFS need to be in the same VPC. So you cannot really launch it outside of a VPC, or if your EC2 instances are not in that specific VPC, they don't have access. So this is all in the context of a VPC and a subnet or subnets that are available within the VPC. So that is the most important thing. And this is also relevant when you're doing hybrid, because when you actually do a direct connect or when you do peering, you're going to connect your on-prem data center to the same VPC. And then the same EFS file system becomes available. So VPC is the boundary within which the EFS and all the consumers of EFS would live. So let me click on customize, and I'll show you additional configuration here. So you can configure backups, and you can do all of this. And then in the next step, you can basically choose what are the subnets that are available here. So it's a good idea to basically launch this EFS file share in all the available subnets. So by default, all the subnets are selected here. So you have AP South 1A, 1B, and 1C coming from the Mumbai region. And then these are associated with one subnet. And there is also a security group that is associated. The default security group is good because it automatically allows the traffic to come from any consumer, any resource that belongs to the same VPC. So that is the network configuration. And then in the next step, you can actually define a policy. So this policy is going to provide either read-only access or provide root access. So more on this later. This is actually much more granular if you use IAM. So to save time, I have gone ahead and created a file system called ML. Now let me show you how this actually looks like. So the most important thing after you created the file system is to define the access point. So here I have created an access point. For example, the root directory path is /ml. So give me a second. I want to turn off a plugin that I have, which is going to be annoying. So I'm going to, okay. So, so this is going to be exposed as /ml to the outside world. So that is the root directory path, and it holds a lot of significance. And then we also need to create the access, particularly for the POSIX user. So as you know, in Unix and Linux, basically file system permissions are based on the UID, group ID, and so on. So here it's a good idea to give an arbitrary user ID, group ID, and then also define the permissions for that specific group ID. So later on, when you want to transfer the control, you can actually run chown from the EC2 instance to basically make this user and this group the owner of the file share. So this is very important because this is how you will let the file system become available in a variety of environments. So any any user that is using within EC2 will first own that, depending on, for example, if you're using Ubuntu or EC2 user, if you're using Amazon Linux, you will take control of it. You modify the file system, you add directories, you delete files, do whatever, and then you set the ownership again to this specific POSIX user. So that is how you manage, and that's the most important thing. So now at this point, we have a file system called ML. It's exposed as /ML, and then it is associated with a POSIX user with user ID 1001, and we also define the root permissions, which is 750. And of course, this is available in all the subnets of the VPC. So that's all you need to do when it comes to the EFS configuration. Now, all of this can be done from the command line as well. You can actually use the AWS CLI, or if you want to do programmatically, you can use CDK, the Cloud Development Kit. But I'm actually walking you through the console because it's more interactive and clarifies a lot of concepts. Perfect. So we are done with the first step, where we have gone ahead and created the file system called ML. And now the next step is basically mounting this in an EC2 instance. So we launch an instance. Amazon Linux is a good family, AMI to use, and we'll use the T2 medium family of the instance. Then here in the configuration details, you obviously leave the default. It is targeting the same VPC. You don't need to touch the subnet. Everything remains the same. The most interesting thing here is add file system. So when you click on add file system, it automatically picks up our ML EFS file system, and you can modify it here. It is basically going to show up within the VM in this path /mnt EFS fs1. You can modify it here. Now, the moment you select this, the cloud init section, which is going to pass some user data, will add everything to basically mount this file share. So if you notice, all the commands that you would typically run at the command line to install NFS and mount an NFS share will be automatically created for us. So if you notice, it is installing NFS utils, and then it is going to mount the file system. It will manipulate FS tab to add a permanent entry to make sure that the NFS share persists, the reboots, and so on. And then finally, it gets mounted and becomes available. So choosing this is going to add the user data, which is cloud init. So you can watch this here. So that's the important aspect. And then behind the scenes, it also adds an IAM role to make sure that this EC2 instance has enough permissions to access the underlying file system. Then we leave the defaults, configure the security group. It's again a good idea to make sure you're selecting the default VPC security group, because this is going to give all permissions and all access to the EFS share. So we select that and then review and launch. So finally click on launch. Now again, I don't want to wait for the instance to get created. I have again created an instance of exact same. It's an Amazon Linux 2 AMI T2 medium, and you can actually SSH into it from this public IP address. There is no EIP, elastic IP, that's not required for this. We'll come back to that in a second. So now what we have done is we basically launched an EC2 instance with EFS automatically mounted. So how does this look like? Well, let's go ahead and SSH into the box. So now I'm going to SSH, and the first thing that I'm going to do is go to MNT directory, and there we see EFS, and within EFS there is FS1. And this is the, if you have not configured, this is basically a blank directory. Now this is where all the magic happens, right? Now once we have the EFS share available within the file system, we are all set to go ahead and run the training or bring the model. So what kind of a model are we going to copy, and how do we basically port an existing model? Well, I want to show you a quick demo. So I have a simple Python program written using PyTorch and Flask. So this is currently running on my local host, and what it basically does is, let me show you a couple of images. So I'm going to pass an image of a dog. That's a cute dog. So I'm going to pass this image to the model, and it's going to detect the object. And similarly, I have a flower.jpg, which is going to show us a sunflower or a daisy. So one of those flowers. Now, the idea is to actually use the machine learning model to classify the input image. So, this is the command I'm going to run, which is curl, and I have already stored these images in a public S3 bucket. So, you can actually see them in my S3 console. So where is my S3? There we go. So within the S3 console called mi2 demo bucket, you'll see dog.jpg and flower.jpg. They are publicly available. Now what I'm going to do is simply call this endpoint by passing the URL of the dog image. So now it actually comes back and tells that it is a Maltese dog with a probability of 88%, which is pretty good. So it is able to classify the input image. Now let's send a flower.jpg, which is also available in the same uh, S3 bucket. So now it's going to come back and tell us it's a daisy flower with 99% accuracy, which is pretty good. So this is basically the model that I want to host in Lambda. And I'll take the route of EC2 to basically set up everything within the instance. So now this is my local model. If you're curious, I can also show you how the code looks like. This is a typical ResNet classification program in Python. Obviously it's a pretty straightforward one. Now what I actually do is, instead of downloading the model, so actually PyTorch has a model zoo called the Torch Hub. So you can download it every time you are launching this. But in Lambda, what happens is, every time you are invoking the Lambda function, it is going to download the ResNet model, which is going to take a long time. So instead of downloading it from the model zoo every time the function is invoked, I want to cache it. So what I have done is, I actually downloaded the pre-trained ResNet model, and this is the pre-trained ResNet model PyTorch artifact, and I'm going to load it dynamically. So instead of downloading it every time, I am caching it and loading it from the file system. So if you look at my models directory, there are two files here. The first one is actually the labels. So here you can see there are a lot of labels formatted in JSON. And then this is basically the PyTorch artifact, which contains the ResNet model. They are not really big, but the idea is to avoid any kind of download that would take when you hit the Lambda function endpoint. So that's the model, and basically I want to take this infer.py, whatever is running in my local host with Flask. I'm going to turn this into a Lambda function. That is pretty straightforward, and it's a no-brainer. But what is challenging is, where do we get this model from? We don't want to download it every time from the PyTorch hub or an S3 bucket. So that's where EFS comes in pretty handy. So we're going to take the route of an EC2 instance, and I'm going to simply SCP my pre-trained model, the labels, and even the program. So what do I do now? Well, now that my model is ready, I'm going to switch back to my EC2 instance, and I'm going to run a couple of commands, right? So here, the first thing that I'm going to do is, let me increase the font size a bit. So I'm going to first own the directory, right? Now, when I actually do this, I take control. I become the owner of this file share. Now, once I become the owner, I install the PyTorch library by using -t and the mllib Of course, I would have run mkdir to create the lib and ml folders, but that's not the point. The point here is I can use pip to target an existing directory when installing Python modules. Now, this was a big revelation to me. I didn't know that it is possible to target an existing directory through pip. And once I knew this, it became very clear to me on how to share libraries between EC2 instance and a Lambda function. So we're going to run this command. Now, obviously, when we run this, I'm not going to run. It's going to take a while. It's actually pretty time taking. It may take anywhere from 10 to 12 minutes. So what actually happens is within the lib directory, you will see there are a lot of modules, Python modules that get installed. Now, this is the outcome of this command. So basically, we are creating the lib directory with pre-populated PyTorch modules and all the dependencies. Perfect. Now, the other option is to use a virtual environment and run pip install. But I found this to be more faster and more efficient than Python virtual environment. I ran into a lot of issues when I actually used that. So that is the next step. At this point, we installed everything that we need. And once we are done with the pip install, we'll give back the control to the arbitrary user who owns this file share. And that is the user who has the UID of 1001. Now, this command will relinquish the control of the EC2 user to the arbitrary user that was defined when we created the file system. Perfect. So now that is done. Now, the next step is to basically move our fully trained model into a directory called models. Now, you see the ResNet file here. It is exactly the same file that you see here. So I have simply done an SCP to move this file from my local file system along with the label file into EC2. So it has the same label file, okay? The ResNet image, the ResNet model, and all the labels that are expected. I think this is trained with an ImageNet data set. So we have the model file and the label file. Perfect. So now we have everything that we needed. Now, alternatively, I could have trained the model in my EC2 instance, but I didn't want to do that for a few reasons. One, ideally, I want to run this in SageMaker, or I want to run it elsewhere and use EC2 only as a bridge to move my artifacts from an external environment to Lambda, because I need to mount the EFS file system. And that is the job of this EC2 instance, nothing more, nothing less. It acts as a conduit, as the bridge between our local environment running PyTorch and Lambda. And once that is done, we can actually terminate the instance, or we can just stop it. All right. So that was the job of the EC2 instance, right? And this is the EC2 instance that's running. Now, again, pretty straightforward. There was nothing. The only magic happened when we ran pip3 install with a -t. All right. So now we have the file system fully populated with everything that we need: the PyTorch dependencies, the model file, fully trained model file, and the labels. So now the next step is to go ahead and create a Lambda function that can access all these assets. So what we do here is create a function. Let's call this mi2. Choose the runtime as Python 3.8. And then the most important aspect here is the execution role. Now, when you're creating a Lambda function that needs access to the EFS file system, you need to create a specific IAM role. So let me show you how that IAM role looks like. So here is my IAM role called Lambda EFS. And this has two important policies. One is it has the Lambda VPC access execution role. What it basically does is it will it will have access to the logs, because ultimately we want to access the logs through CloudWatch. So we need that. And then because this is running inside the VPC, and to basically make sure that it is able to make outbound calls, or even to connect to another resource running in the same VPC, it needs access to the ENI, which is the Elastic Network Interface. So we have given permissions, or basically a policy that has permissions for creating the ENI, describing, deleting, managing the life cycle of the ENI. This is required because the Lambda function would technically attach itself to a subnet, and that subnet needs to have an ENI with or without a public IP address to access the resources. In our case, the EFS file share. So this is the policy that's required. And then we also need an explicit policy to access EFS with permissions that say client mount, client write, and describe mount targets. I put resource as start. We can basically access any EFS file share. If you want to be very restrictive, you can also put the ARN of the EFS file system that we created, file share that we created. So that is the basic IAM role that you need to create at the minimum. Now I'm going to associate my Lambda function with that IAM role. You can go to advanced settings and choose the VPC. Now this is the most important. So choose the same VPC. In my case, it is a default. There is only one VPC. And then it's also a good idea to have Lambda function run in multiple subnets of the VPC for HA. So if for some reason, if one of the AZs become unavailable, Lambda will continue to run in the other AZs. So it is a best practice when it comes to AWS, and Lambda is not an exception. So we make sure that Lambda runs in every subnet within the VPC. And then we also chose the security group. Now, without this, Lambda cannot access other resources in the subnet. So we associate this with the default subnet. That's it. Now, these are all the steps required to create the Lambda function. Now, let's click on create function. Now, this is going to create a Lambda function. Now, once this is initiated, you can do a couple of more things. One is add a file system. Now, this is a very crucial step. So click on add file system, and it automatically picks up ML, because we are now using the same subnet, and it can pick up the file system that is available within the same account and also same VPC. And then choose an access point. Access point is /ML that we created earlier, with the POSIX group ID and everything that was configured. That is the access point. You can actually create another access point if you need, but we are good with this. And then I want to expose this as /MNTML. Now, this will basically make sure that the EFS file system shows up in this directory. Now I'm going to click on save, and that is it. Now we have Lambda that is able to talk to the file system, right? So this is the file system. Now we need to do one more thing before we can move over our inference function from on-prem to Lambda. That is telling where the Python libraries are. So for that, you need to add an environment variable. So this environment variable called Python path will point Lambda runtime to the folder, the directory that has the PyTorch dependencies. Now, if you actually look at this MNT, EFS, FS1, ML, lib, now this is the directory that is going to show up here. Now we're going to save this. That's it. Now our function is ready to run the inference. Now, I actually have a fully configured function, again, just to make sure we save time. And this is exactly the same Python function. So if you look at my code, you'll actually notice that Okay, I'll set the syntax to Python just to make it look better. Okay, so now we are loading it from a hardwired path, MNT ML models, followed by the PyTorch model. And then I got rid of the Flask function or the Flask request because we have moved that Flask function to Lambda. So I moved a bunch of lines of code into the Lambda handler, and then we grab the URL that is coming as the query strings parameter, and then everything else remains the same. So this is exactly how my current infer.py looks like. The only difference is this is running on Flask, this is running on Lambda. So obviously, the post handler that is there inside Flask has been converted into the Lambda handler. Everything, the core logic of transforming the inbound image and then performing inference, everything remains the same. It's just that we moved away from Flask to a Lambda handler. Perfect. So now we are actually ready to test our function. So if you notice, this is exactly the same thing, whatever we have done in the previous step. So now what I'm going to do is to create a test function. So I already have a test event here. So if you actually notice, I am sending query string parameters as a JSON payload. It has URL, and then I'm pointing this to the flower.jpg living in the S3 bucket. Now we are doing that because the query string parameter accepts URL as the key. So that is what I'm sending in the test event. So now I can basically go ahead and run the test. Now the first time when we run the test, it's going to take a while. That's because the Lambda runtime has to access the EFS file system and then load PyTorch environment and then load the model along with the labels and perform inference. So it's going to take a few seconds, not really long, but takes a while. So now I send the flower.jpg. If you actually look at my code, so that is flower.jpg, I'm going to change this to dog.jpg. Now you notice that it is coming back with the same JSON response that says the flower is a daisy flower with 99% probability, which is great. Now let's apply another test event, this time pointing to the dog.jpg, and it's going to be fast. And it comes back and tells it's a Maltese dog. Perfect. So now we are able to successfully invoke the Python function deployed as a Lambda serverless function, right? Now, the next step is obviously to add a trigger. So we'll add a trigger, and this trigger is going to be an API gateway. So this API gateway is going to create a HTTP API, and I'm going to keep it open, and I don't want to embed any security token, and we'll click on add. So this is going to create a nice API gateway for our Lambda function. Now I have already created a Lambda function that says infer. Now infer API. So both of them are pointing to the same. So now we have a API gateway that is pointing to the AWS Lambda function. So now we can actually grab this and do a curl by passing the appropriate URL. So this is the command that I want to run. So this is the API gateway, and this is the URL which is coming from the S3 bucket. So let me copy this and run it in my terminal. So now this is going to hit the API gateway, and from there it will go into the Lambda function, and then we should see the results. There we go. Takes a few milliseconds. extremely fast. Now I can play with other images. I only uploaded 2, but you can eventually pass any image and it should be able to predict. So this is pretty cool. Now from 0 to 60, we have done everything in less than 30 minutes. Now from creating the EFS file share to launching an EC2 instance to installing the dependencies and training the model and moving it over, then configuring a Lambda function to point to the EFS share, test it, and then attach an API gateway and going live. Fantastic. Now this is, again, as I mentioned, is a pretty cool way of creating a MLOps pipeline, which will always have an up-to-date model. And this is exactly what we have done. So this was step 1. This was step 2. This is step 3 and step 4. And again, for your quick recap, these are the steps. We created an EFS file system, mounted it, installed the dependencies, trained. Again, actually, I cheated here. I didn't train. I used a ResNet model. But technically, yes, you can train a model and copy the model file, and launch and configure an AWS Lambda Python function, attach an API gateway, invoke the API. We have pretty much gone through all these steps. The most important element here, which I missed while I was learning this, was the security aspect. If you don't have an appropriate permission for Lambda to talk to EFS, it will fail. It will never find this file share. That is one. Second thing, if you're familiar with Python, you know that the Python path can override the default lookup directory. So this is a pretty cool mechanism to point Lambda to a custom environment, to a custom directory that has all the dependencies. Third thing that I really struggled hard was the fact that Lambda couldn't make an outbound internet call. That's because, remember, Lambda is running in the context of VPC, and the subnet on which this Lambda function is running didn't have an NAT gateway or a mechanism to make outbound calls. So technically, you are supposed to configure a routing table in your VPC and basically have the outbound internet connectivity configured. Now, again, I didn't have enough time to configure the outbound internet connectivity through the right mechanism. So I have taken a shortcut. So what I've done is I have basically added the Elastic IP to all the subnets to turn them into public subnets. Not a good idea. Don't do this at home. This is not a production ready use case, but it gives us a nice shortcut to quickly test this. If I release my Elastic IPs associated with each of these ENIs, and these ENIs are associated with these subnets, now the Lambda function cannot make an outbound call. So to ensure that Lambda is able to make an outbound call, I have gone ahead and attached an EIP to the ENI associated with every subnet. The best practice for that is to use an internet gateway or the NAT gateway and configure a routing table for your subnets. That is how it is supposed to be done. But I have taken the shortcut of creating an EIP for each ENI and circumvent this whole mechanism of creating the gateway. But again, not recommended. Don't do this. This is good for a demo, not for production use.